state and prove the subgroup criterion test. Well, the subgroup criterion test gives us a one-step solution, actually, to proving that a non-empty subset is a subgroup of G. So let's say let H not be empty. In other words, there's something in there. Let H not empty be a subset of a group G. The subgroup criterion test tells us that H is then a subgroup of G if and only if, let's see, I think I'll write it this way, XY in H implies XY inverse is in H. The operation is just, we just make it look, we use multiplicative notation, but it's really any group operation. Now, I would note that if the operation happens to be addition, matrix addition, addition of real numbers, then we would write this when we were doing that particular proof, we would write X minus Y is in H if the operation in G is addition. All right, now we want to prove this, and the first thing I will do will be to get, well, let's go this way first. That's obvious. If H is a subgroup of G and X and Y are elements of H, since H is a group on its own, we know XY inverse is in H because H is a group. So really, in that direction, there's not much to prove. So our challenge is to go this way. So suppose X, Y, X comma Y in H always implies that X times the inverse of Y is in H. We want to prove that H is a subgroup. Well, of course, first of all, we have the operation is associative because G is a group, and we know that the operation is associative in G. So let's just say associativity of the operation is inherited from G. It's a subset of G. And G is a group. All right, so now let's pick an element in there. Let's see, we know that H is not empty, so let's let A be an element of H. Not being empty gives us permission to choose an element in there. And on the basis of being able to choose an element in there and using our, let me go back up here and show you what we're going to use each time. This right here, let me put a box around it in yellow. Anytime we can pick two elements in H, we know that one of them times the inverse of the other is in H. Let's call this star, and when I use it, I'll say by star. And each time you go back and see exactly how I have used star in order to get all these different parts of the proof. The first thing we did was we picked an element in there because it's non-empty. Well, then by star, I'm using star, A inverse is in H. In other words, E is in H. The identity of G is an element of H. Notice when I use star there, I have X I'm using as A and Y I'm using as A. Nothing up here said that X had to be different than Y. And we can say also by star, we've got this A. Let's say, well, we've got E in there now too. So we can say that E, A inverse, which is A inverse, is in H. So we have inverses and we have the identity. We have associativity, and all we need is closure. In other words, the fact that the operation is also a binary operation on H. So that means it must be closed under the operation. So to get closure, let's let A and B be in H, and of course we want to show that AB is in H. Well, I know that B inverse is in H because we proved it above. So by star, AB, which is A times the inverse of B inverse, is in H. So we get closure. Notice in this we needed B inverse in H so that we could use star to get AB in H. All right, so we showed the 4 group properties, and we can say, therefore, H is a subgroup of G. Question 2, we have an arbitrary group, and I asked you to define the centralizer of a group element A. So the centralizer of A is the set of all X in G, the set of all group elements, such that they commute with A. XA equals AX. So don't memorize these things as symbols. Read them. Make these sentences in your mind. The centralizer of A is the set of all X in G such that XA equals AX, the set of all group elements that commute with A. We want to prove it's a subgroup in part B, so we simply let X and Y be in the centralizer of A. Now we're assuming that A is some fixed element of G. So we let 2 elements be in there, and all we need to do is show that XY inverse is in there. Well, when we let X and Y be in the centralizer, we then interpret what that means. Then XA equals AX and YA equals AY, because that's what it means to live in the centralizer. You're using the definition of what the centralizer is. We want to show that XY inverse is in there. So we want to show that XY inverse commutes with A. Now, YA equals AY, let's, since YA equals AY, let's multiply on both sides by Y inverse, on both on the left and the right hand side of both expressions. So this implies multiplying on the left by Y inverse, YA, Y inverse, equals, I'm doing 2 steps at once here really, Y inverse, AY, Y inverse, which gives us, when you cancel here, Y inverse is the identity, we get AY inverse equals Y inverse A. And this was important to us because we needed to get Y inverse in the centralizer before we could get X times Y inverse in there. So now I want to get XY inverse in the centralizer. In other words, I want XY inverse to commute with A. So I'm going to take several, I'll take around the long way so you can see how we use every step. XY inverse times A is equal to, because the operation is associative, X times Y inverse A. Y inverse commutes with A, as we just showed, and then so I have X times A y inverse. Using the associative property again, I have XA y inverse. And finally, commuting, we know x is in the centralizer, so XA is equal to AX times y inverse. And now, using the associative property again, A times XY inverse. Therefore, A commutes with XY inverse, and we can say, therefore, X times Y inverse then is in the centralizer of A. We showed that the XY inverse satisfied the rule for being in the centralizer of A. And we can say then that the centralizer of A is a subgroup of G. And the third part of the second problem was to do an example, find the centralizer of a group element, and in this case a matrix in the general linear group with real entries. Well, we could define it. You don't really need to say this, but we could write, just to make sure that you understand the definition, the centralizer of that matrix will be the set of all matrices in the group that commute with A. So we want all the matrices B such that BA equals AB, where A is this fixed matrix. Well, let's see what the matrix B, how we could characterize these matrices. If we take a matrix A, B, C, D and require it to commute with our given matrix A, then this would be true. And I want to find out what kind of restrictions would be on A, B, C, and D. To live in our group, the general linear group, all we know is that AD minus BC, the determinant, is not 0. But there will be far fewer that commute with this particular matrix A. So let's see. If I multiply on the left here, just multiply it out and we get B and then minus A. And then we have D and minus C. And if we multiply in the reverse order, we have minus C and minus D, and then we have A and B. So we want these to be equal. Well, this would imply that B is the same thing as minus C, that minus A is minus D, so let's just say A is D. So we know that these are going to be the same. A and D are the same. And we have D equals A. Well, I already wrote that down. And minus C is equal to B. And I already wrote that down. So we have this will characterize the matrices that we want. So let's write a form for any matrix B that will commute with A. I think I'll write, let's let the upper left entry be X, and then the lower right entry will be X, and B is equal to minus C, so I could put Y here and minus Y here. So our matrices that commute will look like this, and I didn't take off credit if you didn't say this, but we have to restrict, the determinant has to be non-zero. So the determinant here would be x squared minus a minus y squared. So that's x squared plus y squared is not equal to 0. Well, that means that B is not the 0 matrix, and any other one that has the entries like this will commute. So this is what I wanted you to do, was to set up an equation and set the corresponding entries equal and see what had to be true. If you have trouble multiplying matrices and you don't remember this, that's up to you to go back to your linear algebra text or to look it up online, because this is we expect that you know this by the time you take modern algebra. Okay, problem number 3, we want the center of the group of matrices with non-zero determinants. So in other words, we want to find all matrices A in GL2R with non-zero determinants such that if A is equal to A, B, C, D, we need to name some entries. A commutes with this matrix here, so A, B, C, D times, excuse me, you guys, I'm not going to do this over though because I'm too busy. So let's see, prove that the center is equal to this. All we will do is prove that these matrices commute with all A in the group. So let's just say for all A in GL2R, if A is equal to this, notice that it commutes with this matrix. X, 0, 0, X, A, B, C, D. Compute this and you get AX here. And then you have BX here. And here we have CX. And here we have DX. And on this side you'll get the same thing. We have AX, and then BX, and CX, and DX. So you could say this is true because they have the same entries. So I think I will stop there. There's actually something more that you should do in this problem, but none of you did it, thank goodness. And I didn't think of it when I wrote the question. You really should prove, all we really did there is prove that this is a subset of the center. And what we would need to do is show that there are no more matrices that commute with all other matrices. But I think I'm not going to do that right now. I don't like this question too well, but fortunately it was one you all did very well on. So proving that those matrices commuted. This question was missed by many of you because you didn't see. Well, I forgot exactly where I was here, but if you want to prove, let's write this in a different color. To prove G is abelian, let, well, you could let A and B or X and Y, whatever, B and G, and prove that AB is equal to BA. The reason that almost all of you did not prove this is because you didn't think of the definition of abelian. The first thing you do is get your plan, and it always involves using the definitions that you have been given. So we want to do exactly that. And you'll see it's not too hard once you realize that this is what you have to do. So let's let A and B be elements of G. And I gave you a hint. I said use the fact that AB quantity squared is equal to E. Every non-identity element has order 2. Every element of G could be, it doesn't say it has to be a group of order 4, as some of you thought. You were thinking back to the problem that you did before and just memorizing what we did with those elements. But it's the definition you want. So let A, B, and G, and let's go from our hint. We know that AB times AB is equal to the identity. And we also know that A squared is the identity and that B squared is the identity. So this is just kind of, thinking here, but this is what we're given, that every non-identity element, squared is E. So let's set those equal. AB equals AABB. And now multiply on the left by A inverse. Here, let me change colors here. I could multiply on the left by A inverse and on the right by B inverse. On the left by A inverse, on the right by B inverse. And what do we get? Well, A inverse A is the identity. This gives us immediately, this gives us, it's not changing color. There we go. This gives us, when we cancel, that BA on the left is equal to AB on the right, and we're done. G is abelian. So again, what I think all of you, if you had known what you wanted to prove was that AB equals BA, which should be immediate because it said prove the group abelian, then I really think you all could have gotten there, because you had things like this written on your page, but you never got around to showing what we needed in order to prove that the group is abelian. Here, first we define the conjugate subgroup. H is a subgroup of G, and if we pick any element of G, it could be in H or out of H, and conjugate the subgroup by it, we call that GH, G inverse. H is a subgroup, G is any element of G, in or out of H. You can find the conjugate subgroup. And it's equal to, well, it's the set of all G, H, G inverse, where H is in H. In other words, you just take every element of H and conjugate it by G. Multiply on the left by G and on the right by G inverse. G is a fixed element of the group. It's a particular element of the group. And H ranges through the entire subset. So I think I'm going to do C and D before we prove that it is a subgroup, so you can see an example. Let's do part C. Here, H is the subgroup generated by taking powers of R cubed in D6, so it's just R cubed and E. So we get E and R cubed. If you square R cubed, you get R to the 6th, which is the identity. And in this case, we're going to conjugate it by the element HR. So we want HR, H, HR, inverse. Well, all of the elements in a dihedral group that have the H, they are all flips. They all have order 2. We've calculated this many times, but you can just remember that all the elements of a dihedral group that are HR to the K, those are all order 2. So HR inverse is HR. So this set that we're going to be finding is HR, E, HR, and the other one will be HR, R cubed, HR. Remember, because HR is HR inverse. HR inverse is HR because it has order 2. And if you calculate this, of course, there's no need to ever conjugate E by something because it's just going to be GEG inverse, which is E. So you'll always just get E back there. But here we have to calculate a little bit. And let's see, let's go right underneath it here. Excuse me, I've got to find where. Okay, so this is HR to the 4th, HR, And so I'm going to take these two and use our calculation in the dihedral group D6. This will be H, and then R to the fourth H is HR squared times R, and so HH is the identity, and this is R cubed. So in this particular subgroup, we conjugated by an element outside of H, and yet we just got the subgroup back. It conjugated H to itself. And now we'll look at an example where that is not the case in the next example. So let's see, in the next one, K is the subgroup generated by R cubed and H. So here's K. Let's see, I'll switch colors for this one. K is equal to, all right, it has R cubed and H and E in it. So let's put in E, R cubed. When you square R cubed, you get E. H, when you square H, you get E. But it's not just those, because we have to get K to be closed. In other words, we have to generate all the products of these elements. Well, it turns out that, well, you know R cubed commutes with H, so HR cubed is R cubed H, and this is all we get. If you multiply R cubed times HR cubed, you're going to get H. If you multiply H times HR cubed, you're going to get R cubed, etc. So it just has 4 elements in it. Again, K was generated here by 2 elements, so it would be all powers of R cubed, all powers of H, and any products of those powers. So you have to kind of sometimes use scratch paper and make sure you generate out all the elements of the subgroup. All right, now we want to conjugate by R. So R inverse, we know, is R to the 5th in D6. So we're going to go and we're going to multiply R, K, R inverse will be. We just take each element of K and multiply it on the left by R and on the right by R to the 5th. And of course, we get E when we conjugate E by R. Then we will have R cubed, R to the 5th. Then we will have R, H, R to the 5th. And then we will have R, HR cubed, R to the 5th. Just multiply each one on the left by R and on the right by its inverse. So, well, if we carry that out, we will get, just being careful to use your calculation rules in the dihedral groups, we get E, and let's see, this is R to the 9th, and that's the same thing as R cubed. And this, well, that's HR to the 5th, so it's HR to the 10th, HR to the 4th. And this one will be, well, RH is HR to the 5th, so it's going to be HR, just HR. And that's what we get. Now, is that a subgroup? Well, let's see. If we multiply HR times R cubed, we get HR to the 4th, and it commutes. We get the same thing. If you multiply HR times R cubed, you'll get HR to the 7th, which is HR. And you can try. You'll see that, yes, this is a subgroup. This is conjugating K by an element outside of K, and in this case, we get a different 4-element subgroup. The conjugate subgroups will have the same order as the subgroup that you're conjugating, but they often will not be the same subgroup. Sometimes they will, as you see in these examples. Okay, and then let's prove. Now, hopefully you have a better idea of what this conjugate subgroup is. We have a subgroup. We have an element of G that we are going to conjugate the subgroup with, giving us, well, we take each element in H, multiply it on the left by G, on the right by G inverse for all H in H. That's exactly what we just did in the two previous examples. We want to show it's a subgroup, so we start by using the subgroup criterion test. Let X and Y be elements of GH G inverse. Remember, G is a fixed element. Okay, so, well, that means that X is G times some element of H times G inverse. So X is equal to G times some element of H, G inverse, and Y is equal to G times some H, G inverse. If I write it as I just did, notice that it looks like X and Y are equal. So I'm not going to do that. I'm going to say H1 and H2. I mean, they might be the same, but we want to indicate different elements of H, or the possibility of being different. For some H1, H2 in H. If X and Y live in the conjugate subgroup, then X and Y are conjugates of some elements of H. Well, we want to show that XY inverse is a conjugate of some element of H, satisfying the membership rule here. So, well, let's just take XY inverse and just start with it. XY inverse is, okay, well, the obvious thing would be to write G H1 G inverse for X. And then for Y, it's G H2 G inverse. And it's Y inverse, so we take the inverse of that. Now, we were not told anything about G being abelian, so you have to be careful here. Since we don't know if it is abelian, when we change this expression here, we have to be careful. So we have G H1 G inverse, that's our X. And now this I have to take inverses in reverse order. It's G inverse inverse. Well, maybe I should write that. Just, you don't need to write this. You could just write G H2 inverse G inverse. And let me write down, we learned that, well, I'll just write ABC inverse equals C inverse B inverse A inverse. In general, we actually had A1, A2, A3 up to A sub n inverse. If you don't know if the group is abelian, you have to do this in reverse order. Notice why it works, because if I write A, B, C here, the C's cancel, the B's cancel, and then the A's cancel. You don't have to move anything around. All right, so well, this is just G, and so G inverse and G cancel, and we have G H1 H2 inverse G inverse. And I'm going to put parentheses on there. Associative property allows me to do that. And I see that I started with XY inverse, and indeed I got G times an element of H times G inverse. But we need to say that H1 H2 inverse is certainly an element of H, because H is a subgroup of G. And we said above that H1 and H2 were elements of H. So, of course, that's an element of H. And we have, therefore, XY inverse does live in G capital H G inverse. And we can conclude that it is a subgroup. Whoops, excuse me. So we can conclude, therefore, GH G inverse is a subgroup of G by the subgroup criterion test, SCT. We let xy be in there, and we showed that xy inverse satisfied the membership rule of the conjugate subgroup. This one again gave students a lot of trouble because from what I could see, you could not read it. Reading and writing mathematics, you don't want to graduate as math majors and not be able to do that. So I will put more problems each time on the test that are not things that you have already seen. G is a group. H and K are two subgroups of G. Let HK be, and then here's how you read this. Let HK, now you don't know, you've never seen that notation before. These aren't matrices, they're not group elements, they're subgroups, they're sets. HK is, well, it's the set of all products, elements from H on the left and elements from from K on the right. Elements from capital H on the left and elements from capital K on the right. The set of all products HK such that H, the first factor, comes from H and K, the second one, comes from K. Now I use the word factor as if this were multiplication, where it's any group operation. We're using multiplicative notation. If the operation was addition, then this would just be H minus K. Okay, so prove that if G is abelian, then this set HK is a subgroup of G. All right, so we are going to assume G is abelian. And use a subgroup criterion test. Let's let x, y be elements of this set HK. Well then, x is H1K1 and y is H2K2 for some H1, H2 in capital H and K1, K2 in capital K. That's what it means to live in this capital H, capital K. All right, so, well, we want xy inverse, so let's just write xy inverse. We're hoping that we will get it to be equal to something from H times something from K. If it is, it lives in there, and we can conclude that HK is a subgroup. But it depends heavily on being abelian. All right, well, x, that was H1K1. And y is H2K2, and we want y inverse. But now, G is abelian, so you can write K2 inverse, H2 inverse, that's fine. But you could also just write H2 inverse, K2 inverse. I think I won't use abelian right now. I'm just going to write H1, K1, and then I'll do K2 inverse, H2 inverse. That's always true. You don't need to. You could just take off the inverse sign and write H2 inverse, K2 inverse, but you would need to mention because G is abelian. So I just reserved using that right away. And now I think I could just move things around and write H1, H2 inverse, and then write K1, K2 inverse, since G is abelian. You don't have to use 4 steps to move those things around. We know that we can move them around freely if G is abelian. Well, H, K, those are both subgroups of G. So we know that H1, H2 inverse lives in H, and we know that K1, K2 inverse lives in K. So we have shown that xy inverse is equal to a product of elements of H times elements of K. So I can say, I've run out of space here, but I'll just say, therefore, xy inverse does live in capital H, capital K, and we conclude that HK is indeed a subgroup of G if G is abelian. Now on this second part of the question, of course you couldn't get it if you didn't know what HK was. But let's, now that we do, let's write out these subgroups, H and K, and show that HK is not going to be a subgroup because S4 is not abelian. So let's see, H is all powers of the cycle 1, 2. It's a transposition, so when you square it, you get the identity, and H is simply the identity permutation and the permutation that sends 1 to 2 and 2 to 1 and fixes everything else. Similarly, K is just going to contain 2 permutations, the identity, and this one, 1, 3, 2, 4. The permutation that sends 1 to 3, 3 to 1, 2 to 4, 4 to 2, and fixes 5. Now, it's a product of disjoint transpositions, so it too has order 2, and when you square it, you get the identity. So each of these subgroups is just a little 2-element subgroup. But now we want HK, so we form it. We take the identity and multiply it to each element of K, and of course we get the identity permutation and 1, 3, 2, 4. I'm only multiplying on the left in H, right in K. So this was the identity times the identity, and this one was the identity times 1, 3, 2, 4. Okay, well now 1, 2, I want to multiply 1, 2 times the identity, and I get 1, 2. And then I want to multiply 1, 2 times 1, 3, 2, 4. So I'll write that. We have to calculate this one. They are not disjoint. But that's the only one you had to calculate in here. Elements of H on the left, K on the right. You have 4 of them. And so we get, well, the identity, 1, 3, 2, 4, the transposition 1, 2, and let's multiply this here. So I'll put down my 1. 1 is fixed, 1 goes to 3, 3 is fixed, so the product of the 3 sends 1 to 3. Now I go back, 3 is fixed, 3 is sent to 1, and 1 is then sent to 2. 2 is sent to 4, and 4 is fixed. 4 then is sent to 2, and 2 to 1, so I close. So you have to be careful. Multiplying those together, we have 1, 3, 2, 4. Okay, so that is the set HK. But what we want to do is show that it is not a subgroup. And actually, it's very easy to see it is not a subgroup. But nobody, well, there was maybe one person in the class that they calculated this properly. And that was a matter of being able to read it. You have to practice reading, and I would say read out loud to yourself, because you should be able to hear English sentences coming out of this notation. All right, but this is not a subgroup of S4. And the easiest thing to see is, well, you could say the inverse of this element is not in there. That would be fine. You could call this sigma and say sigma inverse is not in HK, because its inverse is a 4 cycle and it's not there. Or you could say HK, that set, is not closed under the operation. Because if you take, for example, 1, 2 and multiply it to 1, 2, 3, 1, 3, 2, 4, you won't get another element in there. This is probably the easiest. You have a 4 cycle in there, and its inverse is 4, 2, 3, 1. There's no other 4 cycles, so you see this is not a subgroup.